Modeling contact between deformable solids is a fundamental problem in computer animation and many other fields. The computer graphics community has made great strides in contact detection and response over the past 2 decades. The state of the art is perhaps best reflected in the incremental potential contact method, or IPC. This algorithm can generate compelling animations for highly challenging contact scenarios. However, there are still limitations with existing formulations that demand further investigation. In this example, a deformable cube is pressed down onto a frictionless surface and subjected to a constant horizontal force. Whereas the cube should remain in motion, IPC generates spurious tangential forces that slow down and ultimately stop the cube. To understand this problem, we consider the case of a single vertex moving at constant distance to a sequence of collinear elements, sufficiently close for collision response to become active. A straightforward way of modeling contact is to select the closest primitive, the first segment in this case, and to construct a penalty function based on the distance between vertex and segment. The contact force direction is then collinear with the segment's normal and remains constant as the vertex moves across the segment. While this approach works fine for collinear segments, it leads to force discontinuities in the general case, as demonstrated in this example. Contact force directions change abruptly as the vertex traverses different segments, resulting in force discontinuity. To address this problem, IPC relies on a superposition of smoothly clamped contributions from a set of active primitives, as indicated by coloring. While this superposition technique removes discontinuities in force directions, it introduces contact energy peaks at segment junctions as shown in the plot on the left. These fluctuations in contact energy, in turn, give rise to spurious tangential forces as shown in the plot on the right. And these tangential forces are the reason why the cube grinds to a halt when modeled with IPC. Instead of relying on single primitive pairs or blending multiple per-element potentials, we show that spurious tangential forces can be eliminated using smooth surface representations. Specifically, we demonstrate that the globally continuous normal fields obtained from implicit moving least squares representations allow us to construct smooth contact energies based on closest point projections. IMLS surfaces have already been explored for modeling frictional contact between deformable objects by Larionov al. However, we make 2 crucial extensions. It now takes self-contact into account and supports robust continuous collision detection to prevent tunneling. More details can be found in the paper. We now examine an inverse design example that highlights the advantages of our smooth representation over the state-of-the-art IPC method. In this scenario, 2 vertices, labeled A and B, slide on a rigid body shaped like a quarter of an annulus. The objective is to control the position of vertex B in order to achieve a target location, A*, for the equilibrium state of the inner vertex A. As shown in the convergence plot, IPC fails to reach the desired accuracy, while our approach converges robustly. This discrepancy can once again be attributed to the contact energy barriers introduced at segment transitions when using IPC. Furthermore, as shown in the inset figure, point A comes to a halt at its closest vertex and fails to reach the target location, A*, shown in red. In addition to these numerical experiments, we demonstrate our approach on a set of challenging contact scenarios between deformable bodies, each represented by IMLS surfaces. Here, an armadillo is falling onto a soft plane under gravity. And in this example, the bunny falls through a torus. To demonstrate we can handle self-contact, we tighten a single knot and a double knot with the presence of friction forces. Finally, let's have a look at the catch of the day for our dear armadillo. Thank you for watching.